Hi guys, in this video we are going to discuss about exercise 1.1, second question, fourth question and the fifth question. In the previous video we have discussed about Euclid's division lemma and algorithm. Let me make this clear for you. A lemma means a statement which is already proved and algorithm means it is a step-by-step process. I hope now you are clear about them. Now let's move on to the second question. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So first of all, to begin the question with, let us take one positive integer. So here let a be any positive integer. It can be either even integer or odd integer. Okay, and b is equal to how much? 6. So on applying Euclid's division lemma here, you will get a is equal to 6q plus r, where 6 is the divisor, q is the quotient and r is the remainder. So q is greater than or equal to 0 and 0 less than or equal to r less than 6. Remainder can be 0 and greater than 0 but not less than 0, right? So r is less than 6. So the r value will be 0, 1, 2, 3, 4 and 5. On substituting this r values in the equation a is equal to 6q plus r, we will get for r is equal to 0, a is equal to 6q. See here, this a is a positive integer, right? And the 6q is divisible by 2. When a number is divisible by 2 means then we can tell that is an even integer, right? Even number. So here also this a is equal to 6q is what? Even number, right? So for the next one, for r is equal to 1, a will be equal to 6q plus 1. Here we can't, this is not divisible by 2. And the next one, for r is equal to 2, a equal to 6q plus 2. Just take 2 from both the terms commonly outside. So 2 equal to 3q plus 1. So directly we can divide the term with 2, right? So the 6q plus 2 is divisible by 2. So obviously this is an even integer, right? And for r is equal to 3, a value will be equal to 6q plus 3, which is an odd number. And for r is equal to 4, a is equal to 6q plus 4. In both the terms, take 2 commonly outside, which will be equal to 2 into 3q plus 2. So this is also divisible by 2. So this is an even integer. And for r is equal to 5, a is equal to 6q plus 5. This cannot be divisible by 2. So therefore this is an odd integer. So overall we can tell this 6q plus 2 and 6q plus 4 are divisible by 2. Therefore they are positive even integers. And the numbers which are not divided by 2, that is 6q plus 1, 6q plus 3 and 6q plus 5 are what? Odd integers. So basically we can tell any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. You guys can check the result with the normal numbers, integers, okay? So since in question they have given us positive odd integers, you guys know what is positive odd integers, right? 1, 3, 5, 7, 9, 11, 13, 15, everything comes under what? Positive odd integer. Now divide those numbers with 6 and check what is the remainder for those numbers. You will be getting the remainder as 1, 3 and 5. Nothing other than that. Simply you will be getting the remainder as 1, 3 and 5 when you divide the positive odd integers with 6. So Here also we can tell any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Now let's move on to the next question. Question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So here, first of all, let us consider a positive integer a. So let a be any positive integer and b is equal to 3. Right? So on applying in Euclid's division lemma, we get a is equal to 3q plus r. Then how the r value will be? R will be less than 3. So r is equal to 0, 1 and 2. On substituting the r values in the equation a is equal to 3q plus r, we will get for r is equal to 0, a equal to 3q. This is a positive integer. In our question, they asked us to show about the square of a positive integer, right? So we have to square the equation. On squaring both sides of equation a equal to 3q, we will get a square is equal to 3q the whole square, which is equal to 9q square. Now just split the 9 as 3 into 3 and q square. Okay, so 3 into 3q square. Now instead of this 3q square, substitute some integer m. Right? M is some integer. Instead of this 3q square, we are substituting m. So the equation will become 3m. So a square is equal to how much? 3m. Right? Now let's move on to the next step. For r is equal to 1, a is equal to 3q plus 1. Here also we are just squaring on both sides. So a square will be is equal to 3q plus 1 the whole square. This is of the form a plus b the whole square, right? What is a plus b the whole square? A square plus b square plus 2ab. So apply it. So 3q square plus 2 into 3q into 1 plus 1 square. So 3q square will be 9q square plus 6q plus 1. In the first two terms, you see clearly means 3 is common, right? When you take the 3 outside, you will get 3 into 3q square plus 2q plus 1, right? So here instead of the 3q square plus 2q, we are going to substitute some integer m. Okay. Why we are substituting m value as 3q square plus 2q? Because this q is also some integer, right? So just we are substituting the m value for that. So the equation will become a square is equal to 3m plus 1. Right? Now the last one, r is equal to 2. So when r is equal to 2, a will be equal to 3q plus 2. On squaring both sides, we will get a square is equal to 3q plus 2 the whole square. On applying in a plus b the whole square formula, we will get 3q the whole square plus 2 into 3q into 2 plus 2 square. So 9q square plus 12q plus 4. Here we are going to split the last term 4 as 3 plus 1. So you will get 9q square plus 12q plus 3 plus 1. When you see the first 3 terms, 3 will be common. That is, the coefficients will be the multiple of 3. So take the 3 commonly outside from the first 3 terms. You will get 3 into 3q square plus 4q plus 1 plus 1. So here instead of the 3q plus 4q plus 1, we are going to substitute one integer m. So the equation will become a square is equal to 3m plus When you see the equation 1, 2 and 3, the square of a positive integer, that is a square, is either equal to 3m or 3m plus 1. So we can tell the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now, let's move on to the next question. Question number 5. Use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Previously, we have seen about square of any positive integer. Here, we are going to see about cube of a positive integer, right? And here, they have given the form as 9m, 9m plus 1 and 9m plus 8. Here you can't take the divisor as 9. Why? Because the value will be high and the cubing will be difficult. So we are going to take a factor of 9, that is 3. So let a be any positive integer and b is equal to 3. Then on applying Euclid's division lemma, a is equal to 3q plus r. Q greater than or equal to 0, 0 less than or equal to r less than 3. So the r value will be 0, 1 and 2. Now case 1, when r is equal to 0, a will be equal to 3q. Since we are finding the cube of a positive integer, you have to take cube on both the sides. So a cube will be equal to 3q the whole cube. So you will get 3 cube as 27q cube. Since we have to get the final result in case of 9, you have to take 9 commonly outside. So 9 if you take outside means you will get what? 9 into 3q cube. So instead of this 3q cube, we are going to substitute one integer m. M can be any integer, right? So a cube is equal to 9m. Next, case 2. When r is equal to 1, a will be equal to 3q plus 1. On cubing both the sides, we will get a cube is equal to 3q plus 1 the whole cube. This is of the format a plus b the whole cube. So what is a plus b the whole cube? A cube plus 3a square b plus 3ab square plus b cube. On substituting the values, we will get 3q the whole cube plus 3 into 3q square into 1 plus 3 into 3q into 1 square plus 1 cube, which is equal to 27q cube plus 27q square plus 9q plus 1. When you see the first 3 terms, the coefficient is a multiple of 9. So take the 9 commonly outside. You will get 9 into 3q cube plus 3q square plus q plus 1. So instead of this 3q cube plus 3q square plus q, substitute the integer m. So we will get a cube is equal to 9m plus 1. And case 3, when r is equal to 2, a is equal to 3q plus 2. So here also on cubing both the sides, we will get a cube is equal to 3q plus 2 the whole cube. On substituting this in a plus b the whole cube formula, we will get 3q the whole cube plus 3 into 3q square into 2 plus 3 into 3q into 2 square plus 2 cube, which will be equal to 27q cube plus 54q square plus 36q plus 8. So here the coefficients of first 3 terms are multiples of 9. So taking 9 commonly outside, we will get a cube is equal to 9 into 3q cube plus 6q square plus 4q plus 8. So here instead of this 3q cube plus 6q square plus 4q, substitute m. We will get a cube is equal to 9m plus 8. So when we see all the three cases, we have got the cube of a positive integer as 9m, 9m plus 1 and 9m plus 8. So we can clearly tell that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. That's it guys. We have completed exercise 1.1 of chapter 1 real numbers. We will see the next exercise in next video. Thank you.